Welcome to G Fun Facts Online. In the vast frozen regions of our planet, a silent, dramatic transformation is happening. The colossal rivers of ice we call glaciers are moving and melting faster than ever before, and they speak a language of subtle tremors and violent fractures. For decades, we've struggled to understand them, but now, a groundbreaking technology is letting us listen in with unprecedented clarity. We're turning thousands of kilometers of simple fiber-optic cables into a planetary-scale microphone to hear the secrets of the ice. Traditionally, studying glaciers meant placing a few expensive, difficult-to-install seismometers in some of the most treacherous environments on Earth. This gave us a fragmented picture, like trying to understand a symphony by listening to just one or two instruments. But a technology called Distributed Acoustic Sensing, or DAS, is changing everything. At its core, DAS repurposes standard fiber-optic cables, the same kind that bring you internet, into a dense array of seismic sensors. Imagine a single, hair-thin strand of glass stretching for kilometers, capable of detecting the tiniest vibrations at thousands of points along its entire length. Here's how it works. An instrument called an interrogator sends pulses of laser light down the fiber. As the light travels, it hits microscopic imperfections in the glass and scatters back. When a seismic event, like a subtle icequake, shakes the ground, it minutely stretches or compresses the fiber-optic cable. This changes the travel time of that backscattered light, creating a detectable signal. In effect, the entire cable becomes a continuous, high-fidelity seismic sensor. The advantages are immense. A single kilometer of fiber can provide as many as 500 measurement points. Compare that to one traditional seismometer. This density allows scientists to pinpoint the source of seismic events with incredible precision. Installation is also far simpler. Cables can be laid out over vast, otherwise inaccessible areas, while the sensitive electronics are kept in a safe, remote location. This opens the door for long-term monitoring of the most critical and dangerous places, like the calving fronts of massive glaciers. This technology also hears a wider range of sounds, from high-frequency cracks to low-frequency groans that can last for days, revealing the slow, creeping movement of the ice. It's so sensitive, it has already helped us discover new types of seismic waves within glaciers that we never knew existed. So what are we hearing? For one, we're hearing the birth of crevasses. Glaciers aren't static, they are constantly moving, and this generates seismic signals we call icequakes. On the Rhone Glacier, in the Swiss Alps, researchers laid a 1-kilometer fiber-optic cable just under the snow. The high density of sensors allowed them to identify the distinct seismic crackle of crevasses opening up. This is vital, because these cracks allow meltwater to penetrate deep into the ice, lubricating the base and accelerating the glacier's slide towards the sea. The data was so detailed, it also confirmed a type of jerky stick-slip movement in an alpine glacier for the first time, a behavior previously only documented in the massive ice sheets of Greenland and Antarctica. We can also listen to the sound of melting. A recent study on the Rhone Glacier in Switzerland used a 9-kilometer fiber-optic cable to listen to the sounds of meltwater. They discovered that the high-frequency acoustic signals generated by the turbulent flow of water on the glacier's surface could be used to predict the total amount of runoff. By feeding this acoustic data into a machine learning model, they were able to predict glacier runoff with greater accuracy than models based on weather data alone. This gives us a powerful new tool for managing downstream water resources. Perhaps the most spectacular application is listening to iceberg calving. This is the process where huge chunks of ice break off a glacier's edge into the ocean, and it's a primary driver of sea level rise. In a landmark experiment in southern Greenland, a team deployed a 10-kilometer fiber-optic cable on the seafloor in front of the Ekalorutsit Kongjulit Surmiat Glacier. Using DAS, they captured the entire sequence of calving events. It begins with the sound of cracks forming deep within the ice, which travel through the water to the cable. As the iceberg detaches, it generates underwater waves. Then, the massive impact of the ice hitting the water creates small, localized tsunamis, which register as pressure changes on the cable. In just 3 weeks, the cable recorded a staggering 56,000 iceberg detachments, providing a dataset of unparalleled richness. This research has also revealed what's called a calving multiplier effect. The interaction between the melting glacier ice and the warmer seawater at its base increases erosion. This erosion destabilizes the glacier front, which amplifies calving events, leading to even greater mass loss. For years, scientists struggled to quantify this dangerous feedback loop. With fiber optics, it's finally becoming possible. But the consequences don't stop there. When a massive iceberg crashes into the ocean, it generates not only surface tsunamis, but also powerful internal waves that are invisible from the surface. In many fjords, the water is stratified with a layer of cold, fresh meltwater on top of warmer, saltier water below. The calving event violently churns these layers, creating internal waves that can be as tall as skyscrapers. By using distributed temperature sensing alongside acoustic sensing, the fiber-optic cables can detect these hidden waves by measuring the subtle temperature changes they cause as they pass. These internal waves are engines of ocean mixing. They travel for kilometers, breaking over the sea floor and churning the water column. This process brings more of that warmer, deeper ocean water into direct contact with the glacier's face, enhancing underwater melting. This creates another positive feedback loop. Calving causes internal waves, which increase melting, which leads to more calving. This process has been largely overlooked in climate models, and incorporating this new data is a critical step in refining our predictions of sea level rise. Of course, the technology has its challenges. Deploying cables in these dynamic environments is tough, and ensuring good contact with the ground is essential. The sheer volume of data is also a hurdle, sometimes producing terabytes of information that requires sophisticated machine learning to analyze. But the future is bright. Scientists envision drilling deep into ice sheets and lowering fiber optic cables to probe their internal structure. We could also use existing, unused dark fiber telecommunication cables that already crisscross the seafloor, turning our global infrastructure into a planetary-scale observatory. As our world warms, understanding our ice sheets is more urgent than ever. By learning to listen to the whispers and roars of the ice, this revolutionary technology is giving us the tools we need to understand the complex processes that will shape the future of our planet.